sketch the curve y equals 2x squared over x squared minus 1. We're going to meticulously follow the instructions in Note 91 for this. It's a long process, and we're just going to do one example. You can see other examples elsewhere. Step 1, and we have done some graphing in the past. This one just adds a couple of details involving the asymptotes. So, according to note number 91, we start with step 1, where we're going to find the domain of the function. So let's factor the denominator as x plus 1 times x minus 1, and then exclude the values that make the denominator 0. That will be excluding -1 and +1. Now write that graph in interval notation. Everything from -infinity to -1 open, union with open, -1 to 1 open, union with 1 to infinity open. Okay, step 2, let's find the X-Intercept. The way you always find X-intercepts is let y equals 0. We get 0 equals 2x squared. The numerator has to equal 0 for a function to be equal to 0. So solve, we get x equals 0, that's 0, 0. And because the X-intercept is 0, 0, it's also the y-intercept. You learned that back in algebra. Otherwise, we'd have to do the whole process of setting x equal to 0 to find the y-intercept. Step 3, evaluate f of -x, and we get the same as f of x. When we simplify it, that means what we have is called an even function, and you learned that in algebra. And that means that when you graph it, you're going to have symmetry with respect to the y-axis. Okay, step 4, let's look for the horizontal asymptote. We've got y equals a limit as x approaches positive and negative infinity of the function 2x squared over x squared minus 1. It's equal to, before we can take this, evaluate this limit, we have to work on it so we don't get infinity over infinity. So we divide the top and bottom by the highest power of x. That simplifies it to the limit of 2 over 1, which gives us 2. So y equals 2 is a horizontal asymptote. Let's look for the vertical asymptote now. Set the denominator equal to 0 and solve. X plus 1 times x minus 1 equals 0 gives us x equals plus or minus 1. And so that means that the vertical asymptote is found. First, consider x equals 1. Take the limit as x approaches that from the positive side, and take that limit as x approaches 1 from the negative side. First, the positive side. We get 2x squared over x plus 1 times x minus 1, and let x go to 1 positive. We get 2 over 2 times a slightly larger than 0 number, which gives us infinity. And the limit as x approaches 1 from the negative side of 2x squared over x plus 1 times x minus 1 gives us 2 over 2 times a number slightly smaller than 0. That gives us a negative infinity. So you can imagine what this is going to look like, the function will look like at the vertical asymptote x equals 1. We'll have the function coming from the left going downward and from the right going upward. Now the vertical asymptote for the other location, x equals -1, take the limit as x approaches that -1 from the positive side, and you will get 2 over 0 slightly positive times -2, that's a negative infinity. And then you have to consider the limit as x approaches the same number, -1, from the negative side. That's going to give us a 2 in the numerator over 0 slightly negative times -2. That gives us a positive value on the denominator, which means it's a positive 0, gives us infinity. And now again, you can imagine what this graph will look like at the asymptote, vertical asymptote x equals -1. From the left, it will be going up towards infinity, and from the right, it will be going down towards negative infinity. Now, consider the possibility of slant asymptotes. They're called oblique asymptotes. In this case, the degree of the top is equal to 2, and that's not equal to the degree of the bottom, which is 3. So that means there's not going to be any slant asymptotes. You can read about those in your book. Okay, step 5, we're going to take the derivative, and we're going to look about looking for increasing, decreasing situation in the function. So the critical number is found by taking, the critical number is found by considering the derivative of the function. So we first have to evaluate f prime of x. F prime of x, we'll have to use the product rule, the bottom times the derivative of the top, minus the top times the derivative of the bottom over the bottom squared. And we simplify that and get negative 4x over x squared minus 1 parentheses squared. And then we can go ahead and factor the denominator as x plus 1 squared times x minus 1 squared. And then the critical numbers of the function f are going to be the zeros of the denominator plus or minus 1 and the zero of the numerator, which is 0. Okay, so that gives us the ability to divvy up the number line at these values, plus or minus 1 and 0. And that means that we can have 4 different regions to look at. We're going to consider what the sign, positive or negative, of the f prime of x function is in each of these intervals of x values. So we just put the plus on the top and then the 2 pluses on the bottom for the first region for a total of a plus value, positive value. The next region is positive, the next region is negative, and the last region is negative. Now that means positive slope, negative slope, negative slope. So we have this type of leaning. And that tells us that f prime of x will be greater than 0 all the way from negative infinity to 0. Or you can put negative infinity to negative 1 together with negative 1 to 0. And in the other portion tells us that f prime of x is going to be smaller than 0, negative, from 0 to 1 and 1 to infinity. So the function's decreasing. So we have the increase happening on the left where the arrows are pointing up and the decrease happening on the right where they're going down. Step 6, the function f is continuous near x equals 0, not near x equals plus or minus 1. Okay, so we're going to sketch the local max that's located at x equals 1. The sketch tells us that. I want to say the sketch that we just did, along with the fact that the function is continuous near 0 but not at plus or minus 1, that tells us that we have a local max at x equals 0 but not at plus or minus 1. We're going to have to continue this in the next recording because this is kind of a long problem.